We introduced Paris, part-level reconstruction, and motion analysis for articulated objects. We addressed the task of part-level reconstruction and motion estimation for articulated objects from multi-view RGB images. Considering an object without knowing its category, our input is composed of two arbitrary articulation states of the object. At each state, a set of multi-view RGB images with corresponding camera parameters are given. In other words, our input observes the object in two static states instead of tracking its continuous motion. We believe the setting is more scalable since observing objects in static states emerge more naturally without external operator intervention. Our goal is to decouple the static part in blue and movable part in yellow in terms of both geometry and appearance. And we also predict the joint axis and relative joint states with which we can articulate the object to unseen states. Prior work in STF addressed a similar task by learning category-specific prior from STF samples. They can reconstruct the mesh for the object and deform the object to generate new states, but do not estimate motion parameters. More recent work ditto learns an across-category model to reconstruct part surfaces and estimate motion parameters from a pair of 3D point clouds. But this approach is limited in generalization to unseen object categories, and it do not address appearance reconstruction as well. Moreover, these methods require 3D supervision and articulation annotations during training, which is expensive and unavailable at scale. To address these limitations, we designed a self-supervised approach without relying any 3D supervision, semantic, or motion annotations. The key idea is that we separate the parts from two observations by leveraging motion as a cue. Since the motion accounts for the inconsistency between two states, we optimize the motion parameters by registering the moving parts from the input states T to a canonical state T star. During registration, the component that agrees with the transformation is extracted as the movable part, and the one remaining still is extracted as the static part. Specifically, our model is built on neuroradiance fields and will represent each part of the object in a separate nerve. To render the images at input state T, we query the static field with the rays at T to obtain the static part. Then we transform the rays from T to T star to query the mobile field, which returns the corresponding points of movable part at T from its canonical state. By compositing the colors from two fields, we can supervise the render results with the ground truth images from the input states. The reconstruction and motion parameters will be jointly optimized for each specific scene. We systematically evaluate our methods on both synthetic and real data. Here are some qualitative results. Given the two states shown on the left, we reconstruct both geometry and appearance for each part and also estimate the articulation jointly. We observe that our methods can produce clean part segmentations with high-frequency geometric and texture details. Our predicted motion parameters are accurate, so we can manipulate the object to unseen articulation states and render from novel views with high fidelity. More examples and various articulation structures are presented here. Thank you for watching. Please refer to our paper for more details.